In the first chapter, we'll explore some fundamental ways of thinking about data intensive applications. We'll discuss reliability, scalability, and maintainability in detail, and these principles will guide us through the rest of the book where we dive into deep technical details. Many applications today are data intensive as opposed to compute intensive. Raw CPU power is rarely a limiting factor. Bigger problems are amount of data, complexity of data, and the speed at which it is changing. A data-intensive application is typically built from standard building blocks for commonly needed functionalities. For example, databases are used to store data, caches are used to remember the result of an expensive operation, stream processing sends a message to another process to be handled asynchronously, whereas batch processing periodically crunches a large amount of accumulated data. Now, if you are designing a data system or service, a lot of trick questions arise. So, for example, how do you ensure the data remains correct and complete even when things go wrong internally? How do you provide consistently good performance to clients even when parts of your system are degraded? And how do you scale to handle an increase in load? So, while addressing all of these questions, this chapter mainly focuses on three concerns important in most software systems: reliability, scalability, and maintainability. So, let's talk about reliability now. For software, typical expectations of reliable include that the application performs the function that the user expected, tolerate the user making mistakes or using the software in unexpected ways, good enough performance under expected load, and prevents any unauthorized access and abuse. So, if all those things together mean working correctly, then we can understand reliability as continuing to work correctly even when things go wrong. And things that can go wrong are called faults. And systems that anticipate faults and can cope with them are called fault tolerant or resilient. Now, one thing to note here is that fault tolerant doesn't mean tolerating every possible kind of fault. So, if the planet Earth was swallowed by a black hole, tolerance of that fault would require web hosting in space. Good luck getting that budget item approved. So it only makes sense to talk about tolerating certain types of faults. Now, one thing to note here is that fault is not the same as failure. A fault is one component of the system deviating from its spec, whereas a failure is when the system as a whole stops. So, one method of creating or testing fault tolerance is to trigger the faults deliberately, basically killing individual processes without warning. This way, you ensure that the fault tolerant machine is continuously exercised and tested. Now, let's talk about a live example of this technique: the Netflix Chaos Monkey. So, Chaos Monkey is a popular open source tool developed by Netflix for implementing chaos principles within distributed systems. It is designed to randomly terminate virtual machine instances and services within a cloud infrastructure environment. The primary goal of Chaos Monkey is to proactively test the resilience of a system by simulating real world failures and disruptions. Now let's talk about a few kind of faults which can make your system unreliable. Hardware faults. So when we think of causes of system failure, hardware faults quickly come to mind. Hard disk crash, faulty RAM, power grid blackout, someone unplugs the wrong network cable. Anyone who has worked with large data centers can tell you that these things happen all the time when you have a lot of machines. Hard disks are reported as having a mean time to failure of about 10 to 50 years. So, in a storage cluster of 10,000 disks, on average one disk will die per day. So our first response is usually to add redundancy to individual hardware components in order to reduce the failure rate of the system. However, nowadays there is a move toward the systems that use software fault tolerant techniques in addition to hardware redundancy. Moving ahead to software errors. So, we usually think of hardware faults as random and independent of each other. But there is another class of faults which is systematic errors. So, such faults are harder to anticipate, and because they are correlated across nodes, they tend to cause many more system failures than uncorrelated hardware faults. So, let's take an example. A software bug that causes every instance of an application server to crash when given a particular bad input. Now, for example, consider the leap second on June 30, 2012 that caused many applications to hang simultaneously due to a bug in the Linux kernel. Now, these bugs lie dormant for a long time until triggered by a set of circumstances. The software makes assumptions about its environment until the assumption stops being true. So, moving ahead to human errors. Humans are known to be unreliable. So, how to make systems reliable in spite of unreliable humans? You can design systems in a way that minimize opportunities for errors, decouple the places where people make the most mistakes from the places where they can cause failures. Test thoroughly at all levels. Allow quick and easy recovery from human errors. For example, roll out new code gradually or roll back configuration changes. Set up detailed and clear monitoring such as performance metrics and error rates. Majority of the cost of the software is not in the initial development but in its ongoing maintenance. Hence, we should design software in such a way that it will hopefully minimize the pain during maintenance. And to this end, we'll pay particular attention to 3 design principles for software systems. So the first principle is operability. So you should make it easy for operations team to keep the systems running smoothly. Good operability means making routine tasks easy, allowing the operations team to focus their efforts on high value activities. Data systems can do various things to make the routine tasks easy, including good monitoring, avoiding dependency on individual machines, good documentation, and easy to understand operational model, and minimal surprises. The second principle is simplicity. So, you should make the systems easy to understand for the new engineers. There are various possible symptoms of complexity: tightly coupled modules, tangled dependencies, inconsistent naming, and much more. A good abstraction can hide a great deal of implementation detail behind a clean, simple to understand facade. High-level languages are abstractions that hide machine code, CPU registers, and system calls. And the third and the last principle is evolvability. So you should make it easy for engineers to make changes to the systems. Agile working patterns provide a framework for adapting to change.